All generators use induction to create an output voltage. When the output of a generator is connected to a circuit, the induced voltage causes current to flow through the circuit. There are three requirements for inducing voltage. First, a conductor must be available to carry current. The second requirement is a magnetic field. Third, there must be relative motion between the conductor and the magnetic field. In this illustration, a wire is wrapped around a metal ring. The wire serves as the conductor that carries the current that results from induction. The second requirement, a magnetic field, is created using a magnet. A permanent magnet like this one can be used to induce voltage, but the magnetic field it creates is very small. Electromagnets are used to create controllable magnetic fields that are strong enough to induce large amounts of voltage. This is a basic electromagnet. It consists of a coil of wire wrapped around a metal bar or core. When electric current from a source of direct current flows through the wire, a large concentrated magnetic field is created. The wire may be referred to as the field winding because it helps to create the magnetic field. The third requirement for inducing voltage is relative motion between the magnetic field and the conductor. Here's an illustration that shows how voltage is induced when the electromagnet rotates. This electromagnet has a north pole and a south pole. The magnetic fields at the two poles are opposite in polarity. As the electromagnet rotates, the magnetic fields cross the conductor and induce a voltage. We can say that the north pole induces a positive voltage and the south pole induces a negative voltage. Generator output can be represented as a sine wave that is plotted on a graph. On this graph, the vertical axis represents the strength of the voltage, which can be positive or negative. The horizontal axis represents time. As the electromagnet rotates, the relative positions of the electromagnet and the conductor affect generator output as shown on the graph. When the electromagnet is vertical and the magnetic fields don't cross the conductor, the voltage is zero. Now, as the electromagnet rotates through the first quarter of a complete revolution, the output increases to maximum in the positive direction, and then drops to zero again as the magnet reaches a point 180 degrees from its starting position. As rotation continues, the output reaches maximum in the negative direction as the south pole of the magnetic field crosses the conductor. The output decreases again as the magnetic field moves away from the conductor. Let's expand the simplified illustration of a generator to show some other components. The metal bar and the wire that is wound around it can be called the rotor core. In the illustration, the rotor core is connected directly to a DC power source that appears to rotate with the core. However, the DC power source for a generator is usually stationary. One way to cause current flow from a stationary DC source to the windings that encircle the rotating metal bar is to use slip rings and brushes. The slip rings are usually made of copper and they turn with the generator shaft. One slip ring is connected to the negative lead of the rotor winding, while the other slip ring is connected to the positive lead. Inside a generator, the slip rings, the rotor core, and the wires connecting the slip rings to the windings all rotate together. The brushes are typically made of a carbon material that brushes against the slip rings as they rotate. Current flows from the negative side of the DC power source through one brush to a slip ring. From there, the current flows to the winding around the rotor core where it creates a magnetic field. To complete the path, the current flows from the winding to the other slip ring, then to the brush, and back to the positive side of the DC power source. The component of the generator that doesn't rotate can be referred to as the stator. The conductor that is wound around it can be called the stator winding. The ends of the conductor are connected to the power system. The output from the generator we've been looking at is single-phase voltage. Single-phase means that there is only one voltage output. This is because our example has only one stator winding or conductor. However, most generators used in power plants are designed to produce three-phase voltage. Let's see how a three-phase voltage output can be produced by modifying the simplified generator illustration. If we add two more stator windings, voltage will be induced in each winding as the magnetic field crosses the wires. The result is a three-phase output. As the rotor rotates, maximum voltage is induced in each of the three stator windings at different times. This sine wave represents one of the three phases. Maximum positive voltage occurs as the field around the north pole of the electromagnet crosses the first stator winding. Maximum voltage in the second phase occurs as the field crosses the second winding. At this point, the first phase voltage is decreasing. In the third phase, maximum voltage occurs as the field around the north pole crosses the third stator winding. Now, the south pole's magnetic field has crossed the first winding, inducing a negative voltage. As rotation continues, each of the three phases produces alternating positive and negative current that is constantly changing. Here's how the three output voltages look on a single graph. We can see that because each of the three phases produces a voltage, the total output is never zero. This means that a three-phase generator is more efficient than a single-phase generator of similar size. Most generators in the United States produce alternating current at a frequency of 60 cycles per second. This graph of a sine wave represents one cycle of alternating current. A cycle starts with the voltage at zero. To complete one cycle, the voltage increases to the maximum positive value, drops back to zero, then increases to maximum in the negative direction. Finally, the voltage returns to zero again. The rotor has completed one revolution, and both the north and south poles of the rotor's magnetic field have crossed the stator winding in the generator. The number of cycles that occur in 1 second is the generator's frequency and is measured in hertz. So 60 cycles per second equals 60 hertz. It's important for a generator's speed to be consistent. Equipment that uses or produces electricity is usually designed to operate at a specific frequency. If the frequency changes, the equipment can be damaged. There are two factors that control the frequency of the current that is being generated. One is the speed at which the rotor turns. The other factor is the number of magnetic poles in the rotor. In this illustration of a simplified generator, one cycle of current is produced for each revolution of the rotor, so the frequency equals the speed at which the rotor turns. In order to produce 60 hertz, a generator's rotor has to make 60 complete revolutions each second, or 3,600 revolutions per minute, abbreviated RPM. But not all generators are built like this one, with one north pole and one south pole. In this example, there are two north poles and two south poles, so that each revolution produces 2 cycles of current. In this case, the rotor only has to make 30 revolutions in a second to produce 60 hertz. That's 1,800 RPM. Now, under normal operating conditions, the rotational speed of a generator will not change. A generator must operate precisely at its rated speed in order to maintain the required frequency of 60 hertz.